We're very glad to have Aditi with us. She is a fifth-year PhD student at Stanford. Dan Bonnet is working with her, it's not the other way around. Right? And she's going to talk to us about data availability sampling with repair.
Thank you for the very kind introduction, Avi. So I'm very excited to be here, and today I'll be talking about data availability sampling with repair. This is joint work with my advisor Dan Bonnet and Joachim Noy and Malila Nikolenko, who are researchers at A16Z Crypto. And this work was actually started when I did an internship there 2 years ago. Would highly recommend that if you're interested. Okay, so let's get started. But I'm going to take a quick detour on threshold cryptography. We will come back to data availability sampling in a minute. So threshold cryptography allows you to reduce trust by distributing a secret value. So pictorially, let's say you have some secret value S. This could be the key to your Bitcoin wallet. This could be a signing key, or this could be a decryption key for your public encryption key. What you can do with threshold cryptography is split this secret among n parties, with, let's say, with T out of n secret sharing. And now this gives you two key properties. The first is that a quorum of any T shares can do the cryptographic task. So, for example, if this is encryption, then any T parties in your quorum will be able to decrypt any ciphertext. But the key property is security, which says that if less than T parties come together, they'll not be able to do anything. So in the encryption setting, you get semantic security for up to T-1 collusions. So this has been very widely used in practice. For example, to build threshold encryption, which is useful for example, encrypted mempools. This is used for secret sharing to do distributed storage on the cloud, and also for threshold verifiable random functions, which are used for randomness beacons in blockchains. But the key question that we've been studying in threshold cryptography is something called accountability. The motivating question for accountability is what happens if parties start selling their secret shares to some adversary. So in the threshold decryption picture, let's imagine that an adversary comes in and offers to buy the secret shares of two parties in your quorum in exchange for $100. And now let's say that they go ahead and sell their secret key shares in some form to the adversary. So this green box denotes whatever type of information they sell to the adversary. So we clearly can't stop parties from doing this because they have the secret shares. They can do anything they want with that. But what we would hope for is some notion of traceability. So for example, in this picture, if a whistleblower comes in and tells us that this green box was leaked to me by some parties, then we should be able to trace this box back to the parties that leaked it, in particular parties 1 and 2 in this example. So this is sort of like the high-level picture for traceability or accountability in threshold crypto. And actually we've seen like in some of our works that this turns out to be impossible to achieve for standard threshold crypto primitives. And this problem has given rise to a lot of recent research on constructing threshold cryptographic primitives which achieve accountability by design. So for example, we have accountable threshold signatures which were proposed in 2001 by Reza et al. But recently there's been works on getting stronger security properties. Then recently this notion of accountability in threshold decryption was formally defined in 2024, and there's been a flurry of follow-up works to get better efficiency and security properties. And two other lines of work are accountability in secret sharing, and the last one is in threshold VRFs. And if some of you are coming to Eurocrypt, I will be presenting two of these works there, so hope to see you there. And there are tons of open questions in this space of accountable threshold cryptography, and I'd be happy to talk more after the talk. Any questions on the accountability aspect? Okay, so with that, we're now ready to move back to the original topic for today's talk, which is data availability sampling. So I'll start with consensus because that forms the core of all blockchains today. So just to pictorially show you what consensus looks like, we have a bunch of validators on the network. They look at a pool of transactions coming in, posted by users, and they look at these transactions, they run the consensus protocol, and then they output an ordering on these transactions. So the list of like blue, green, and red transactions is the order. And then the execution layer of your blockchain can go and execute these transactions in precisely this order. So this is what consensus looks like. But the problem is as more and more transactions keep coming in on the network on the left side, this consensus layer quickly becomes a bottleneck because all consensus protocols have a quadratic amount of communication and computation involved. So there is a big open question in consensus literature to how to scale consensus to handle more and more transactions to achieve higher throughput for blockchains. So one technique that has been proposed to scale consensus is something that we call decouple ordering of transactions from the dissemination. So let's see what this means. Again, we have a bunch of validators on the network, and we have a pool of transactions coming in from the left. But now the main thing we'll make is we'll also have these public references to the transactions, which I'm denoting as the paper clips here. And for consensus, we'll only look at these public references, we'll not look at the full transactions. In parallel, what we'll do is we'll have something called a verifiable distributed storage service, wherein we will actually store these transactions, the full transactions. What will happen for consensus now is the validators only have the paperclips or the references, but before running consensus, they'll just go and verify with the verifiable distributed storage service that the actual transactions corresponding to these paperclips are actually being stored. Once they are convinced that they're being stored, they'll just run consensus on the public references and give you an ordering on those references, so just the paperclips. And then the execution engine takes this ordering of public references, and then it goes and gets the actual transactions from the storage service and goes and updates the blockchain state based on that. So here the key reason why we're able to scale consensus is now for consensus you only need to worry about the public references, which are much smaller than the transactions themselves. So like let's say if the public references were like 5% the size of the transactions, you can now handle 20x more transactions with the same level of efficiency in consensus. So this is a high level picture of what I mean by decoupling the ordering of the transactions, which is the consensus part, from the dissemination of the transactions over the network, which is being done by this distributed storage layer. Any questions on this high level picture?
Yeah, that's a good question. So if you do that,
yeah.
Couldn't you run into the issue where some of the public references you're ordering, you don't know whether they will like successfully execute, like whether they are a transaction?
Good. Yeah. So that's exactly why we need this verification step first. So the validators will first verify, like based on whatever verify looks like for your distributed storage service. Right. So they'll first verify that guarantees under some definition that in the future you will actually be able to retrieve the transaction if verification succeeded.
Right. But
yeah.
This verifies that retrieval will happen in the future.
Yes, at any point in the future.
But it doesn't verify the content of the transaction.
Oh, that's a good question. Yeah. So actually what will happen, like when we see the formal definitions, there will be a commitment. So the public reference you can think of as a binding commitment to the transaction. So like this verification will correspond to the binding commitment. So you will know that it's actually the data behind this commitment. That makes sense? Yeah. So like we will use binding commitments to avoid that problem. Yeah, good question. Okay, so moving on. Oh, sorry, yeah, in the end, the execution layer will just retrieve the transactions from the storage service to execute and update the blockchain state. So let's dive a little bit deeper in this primitive of verifiable distributed storage. In one sentence, this is a distributed system which allows you to verifiably store a large amount of data among a bunch of storage nodes such that we have efficiency. In particular, every single node in your system would need to communicate and store only a small part of the data. So just pictorially focusing on the verifiable distributed storage part, let's imagine we have a bunch of storage nodes. In a consensus picture, actually the storage nodes are the validators themselves, but we don't have to worry about that now. And then we have someone called the disperser. This is usually the block builder in the consensus picture. It gets as input a large amount of data. You can think of this as a single block, for example, containing a bunch of transactions. And then it runs the disperse protocol, wherein it will give a small chunk of this data to every single node in the system. So again, like the data that every node is storing is much smaller than the full input data. And then it also outputs a public reference, which is the paperclip, and this is going to be a binding commitment in our constructions. Then we have a verify protocol. So any verifier can come into the system, run the verify protocol for your scheme to get some guarantee that the data is actually being stored. And this is again done by the validators in the consensus example. And then in the future, at any point, a retriever can come in, run the retrieve protocol, talk to the storage nodes, and get back the full data. Okay. Just to give you some concrete examples of verifiable distributed storage, one example is something called verifiable information dispersal. This is called VID or AVID or ACID if you are familiar with these terms. This was formally introduced by Kashan and Tesaro in 2005, and this has actually also been implemented in EigenDA and Espresso. And here sort of like the key distinguishing feature is that verification is non-interactive. So in particular, every storage node, when it gets the chunk of data it's supposed to get, it outputs a signature that certifies that it actually got the data that it was supposed to get. And then to verify, I just check these signatures. If I see enough valid signatures, I have a reasonable guarantee that the nodes are actually storing the data that they're supposed to store. So then I should be able to retrieve in the future. So this is like a high level of like what VID looks like. I guess one thing here is like you need some sort of honest majority assumption for like enough signatures being able to guarantee retrieval for that. The second example is data availability sampling, and this is what we'll be focusing on today for the most part. And here the key difference from VID is that the verify protocol is actually interactive. In particular, the way this works is that I literally sample random chunks of the data and go ask the storage nodes to give me that chunk. And then I'll output one, meaning I'll accept the verification only if I was able to get all the chunks that I asked for. This is also being implemented in practice in Ethereum and Celestia networks. And this will be the focus of today's talk, but I do want to say that all the techniques that we'll see in this talk also apply to VID pretty much directly. Any questions on the high-level picture? Okay, but the key question that motivated our work is how do we repair lost chunks in this distributed system? So for example, let's say the last node just loses the chunk that it's supposed to store. Or what's worse is that the dispersal in our system might be corrupt and maybe it never even gave the chunk of the data to the last node. Now the reason why this is bad is because this affects the performance, that's the first reason. So for example, if you look at the verify protocol, now all the verifiers can only talk to the first 3 nodes which actually do have their chunks because the last node doesn't have its chunk. Similarly for retrieval, now you cannot talk to the last node, you can only talk to the remaining nodes that are available. So this sort of issue can create bottlenecks in your network because you're only everybody is going to query the same set of nodes, and this is something called griefing attacks. So that's the first reason why you want to be able to repair so that the efficiency of your system remains normal. The second reason is if you don't repair, then let's say in the first week, the last node lost its data, maybe the next week another node loses its data, and then you probably don't even have enough chunks left to be able to reconstruct the data.
Yeah. So is this a concern in dispersal retrieve?
So this is a concern for verify and retrieve.
So if it happens as disperse,
right,
it might be caught by the verify.
Yes. So it can be caught, that's true. But the question is, how do I repair so let's say I identify that this node lost its data. So that's usually easy to do, that it lost its data. Now the question is, how will I actually repair the chunk that it lost? So that's the key question we'll be dealing with today. Yeah, and we'll see how to do that, for example. Yeah. So I guess one more thing I'll say to answer your question is there always exists a simple way to repair that chunk, which is you can collect all the other chunks and reconstruct the original data and then produce that chunk. But that's clearly very inefficient because literally to repair every chunk I lose, I'm going to have to construct literally everything in my network. So the goal of today's work, today's talk will be to show you more efficient ways to do this instead of literally reconstructing the whole data from scratch. So that's sort of the goal of having efficient repair.
So you allow communication between the storage nodes?
Between the storage nodes, yes. But we want to do something better than naively collecting all the chunks and then decoding and reconstructing the data.
Can't you do a Merkle tree thing?
Actually Merkle tree would not actually Merkle tree is even harder to repair.
No, just to detect that there's been a corruption and then
right,
you have a log.
Right.
And you can then, you can identify exactly
yes,
the piece that's corrupt and
right,
take just that.
Oh, so the problem is not to detect that a chunk has been lost. The problem is once you detect it, how do you repair? Does that make sense? So detection is fine because I can just query the node and if it doesn't respond, for example, or the node itself could say oh, I lost my chunk, I want to repair. If it's an honest node, for example, yeah. So the key problem is how do I actually repair once I've detected that this node doesn't actually have its chunk. Good question. Okay, so that's sort of the key motivating question for today.
Can you hear me?
And based on this motivation, in our work we make 3 contributions. The first one is that we have new definitions for data availability sampling. So we are building on the prior definition by Hollanderson et al. In 2023, and we formalize this notion of repair. I'm calling it local repair. We'll see what this means in a bit.
Fan has a question.
Okay.
Sorry, can you hear me?
We can't hear you. Can you message me your question?
Or maybe I can unmute my speaker. Do you think that will work? I can try.
Fan, can you try speaking again?
Hello?
Yes, I can hear you, Fan.
Oh, great. I was just wondering, so do you consider corruption as only unavailability, or what do you also consider the case where the nodes return garbage?
Oh, let's see. So actually in our schemes, we'll always have a commitment scheme. So whenever a node returns something, either it has to give you a valid proof or we just think of it as no chunk. Does that make sense? So there'll always be a way to verify whether the chunk was valid or not. So a node can just it can't just give you garbage because you'll be able to verify that, oh, this is actually garbage.
Yeah,
Does that
thank
answer your
you.
question? Yeah. Good.
Yeah.
So we'll see that in a few minutes, like once I get to the constructions. Yeah, good question. Okay, moving on. So yeah, so the first contribution is just to formally define this notion of local repair, and I will talk about what local means here in a few slides. Oh, sorry. 1 second. Oh, yes, okay. And the second contribution we make is that we propose a generic framework to build data availability sampling, or DAS, from two building blocks. The first one is something that we call a code with locality, and I will formally define this in a few slides, plus a commitment scheme, a special type of commitment scheme, which is an erasure code commitment with locality. So with these two building blocks, we show how you can generically build a DAS with efficient local repair. And the last part is we actually give a new construction of DAS which has efficient repair, where we use this framework and we use multiplicity codes as a code with locality, and then we have a new polynomial commitment scheme. This commitment scheme is interesting. This is like a multivariate polynomial commitment scheme which gives you a lot of efficiency properties like batch opening and local repair. And we believe this can have other applications as well. Wherever you want to use multiplicity codes, we believe this commitment might actually be useful. Okay, so I will start with a brief comparison of our construction compared to Ethereum. So they implemented a PeerDAS system in December in their Fulu fork. So I'm going to compare the metrics from that scheme to our construction. So the first one is node storage. This tells you what's the size of the chunk that every node is storing. And for Ethereum, this is 8 kilobytes. For us, this is only 0.2 kilobytes. So literally every node is storing 35 times less data for every block, basically. The second thing we compare is local repair complexity. So this is all like the key thing we were trying to optimize. So here there are two metrics. The first one is the total bandwidth. So basically we are saying here, let's say some node lost its chunk. It now needs to talk to other nodes to be able to repair its chunk. And the question is, how much total bandwidth do you use over the network to be able to do this repair? For Ethereum, this would be 128 kilobytes. For us, this is just 21 kilobytes. So this is 6 times lower bandwidth usage relative to Ethereum. And again, note like this is, we are getting 6x, but with much less storage at each node. So like it's sort of like getting you both the benefits at once. There is one more metric, which is the number of subnets. So this is particular to Ethereum's network model, where they have this gossip subprotocol, where every chunk of your data is distributed in a different subnet. Maybe I can talk about this after the talk if you're interested. But here, basically, the smaller number of subnets is better in terms of network efficiency. So this is slightly higher for us, about 40% extra. But like for the network that they have implemented right now, this is very reasonable. Like 64 versus 90 isn't a big difference for Ethereum's network implementation right now.
Total bandwidth is across subnets?
Yeah. So like the total amount of communication you have to do over the network, yes, for repairing one chunk. And then we have two more metrics. The first one is sampling bandwidth. So this is saying how much sampling does a single verifier have to do to get some guarantee that their data is being stored. So for Ethereum, this is 16 kilobytes for their parameters, but for us, this is 9 kilobytes. So we're actually also saving on the amount of sampling every verifier has to do. So the overhead for our scheme is actually in dispersal work. So here, essentially, because we're using a bit more complicated encoding and commitment, as we'll see later on, the dispersal work is a bit higher. So especially if you have a lot of cores, then we get about 40% extra overhead. So this is like a bit of a problem, but we believe this is still reasonable because, for example, in Ethereum, the block builders are actually very efficient. So like it's fine even if they have to do 40% extra work because we're getting a lot of savings in other metrics. And the star here denotes that actually the retrieval guarantees of Ethereum are much weaker than our scheme. Okay, so with that, let's now get into deeper details of our contributions. So let me start with a high-level overview of our definitions before moving to the constructions and the framework. Any questions so far? Okay, so let's start with the syntax of the data availability sampling scheme. So this is an interactive protocol between the disperser D and the storage nodes, which I'll denote as N1 to Nn. So N will be the number of storage nodes for the talk. We have a setup algorithm which gives you the public parameters. For example, this could be the CRS for your commitment scheme. We have a disperse protocol which takes as input the data you're trying to disperse along with the number of nodes. And this will give you a commitment com. This is the paperclip that I showed you in the beginning. This is the public reference to the data. And then it also outputs the chunks D1 to Dn. So basically node 1 in your system will store D1, node 2 will store D2, and so on. We have a verify protocol. So these angle brackets denote that this is an interactive protocol. So you can talk to the disperser if it's online. Otherwise, you will talk to the end nodes and you take the commitment as input. And then you will make a few queries, like you'll sample random chunks. And then eventually you'll output a bit B, which is 0 or 1, denoting whether I accept or not. So there's an extra output for verify. This is the tran. So this is basically the transcript of this verification protocol. So like let's say I query node 5 for its chunk or node 10 for its chunk. The transcript that I'll output will be the chunks I got from these nodes. Lastly, we have extract. So this is sort of a notion of extraction to say that like the data has been dispersed. So in terms of syntax, this takes as input the commitment. It takes as input a bunch of transcripts, in particular L transcripts from L different verifiers. And then it tries to extract the data back from these transcripts, or it outputs BORD if it failed. So this sort of syntax was already existed for the prior work, but the two new algorithms or protocols we have in our system are retrieve. So this takes as input the commitment, which is the reference for the data you're trying to retrieve, and you'll talk to the end nodes, and after the retrieve protocol is over, you'll either output the data or abort. The last one is local repair. This takes as input the commitment scheme and index I. So here I'm saying that I'm trying to repair the chunk of party I. And again, I'll interact with a bunch of nodes and I'll output the ith chunk, di, or I'll output BORD.
So you can explain again for the interactive one, for example, for verifying who interacts with whom.
Okay, so the verifier, so like let's say I want to verify whether the data is being stored or not. So I will come into the system and I'll talk to either a disperser if it's online or the end storage nodes which are claiming to store the data.
So I can just talk to this person without talking to the nodes?
If it's online, so like for example, let's say in the block builder example, so if I disperse just right now, for example, in the gossip sub, usually in the beginning of the protocol when the disperser is dispersing, the disperser is also technically a part of the subnets, right? So like you can also talk to that.
So, but
Yeah.
Usually what we want is to talk to the nodes
Yes,
after
yes.
dispersal,
Yes.
and I might talk to all of them or a subset of them.
Subset of them, yeah. So like what will actually happen is I'll just sample random chunks. So I'll only talk to the nodes which are supposed to store that chunk.
And I myself can also be one of these nodes.
I could be, yes. So for example, in the consensus example, actually I am one of those nodes. But there could be other examples. For example, if you think of light clients and blockchains, then I'm not one of the storage nodes. I'm someone separate who's just trying to verify.
And the
Yeah.
same goes for retrieve and local repair.
Right. So retrieve, anybody could retrieve. Local repair, usually if I am the person supposed to store DI, so I am probably the only person who will try to do local repair. Right. So like local repair, usually like only one of the nodes will call, but retrieve and verify anybody can call based on an application. Yeah. Oh, sorry, I'll say one more thing. Actually, local repair, I should mention this, but like an extra application of this is, let's say during retrieval, you only care about one chunk of the data. You don't want to actually retrieve everything. That's another place where local repair could be useful.
Even if you are not.
If you're not in the system, even if you're not one of the storage nodes actually. So this depends on the application. So like I think, I'm forgetting, but like I talked to someone who said like sometimes a user only wants to, so for example, this is like, I'm storing a bunch of blocks in Ethereum, that's what I'm storing, and maybe I only want to retrieve like one transaction from one block. So then this DI is like, oh, maybe I'll recover just that one transaction, I don't actually have to do the full retrieve. So that's actually an extra application of local repair. Yeah, I'm glad you asked that question. Sorry, yeah, you had a question?
Verify works even if D is offline?
Yes.
So,
Yeah.
like, what's the point of retrieve if you can just simulate it using verify and then extract? Like, just...
Yes, that's a very good question. So I think there are two things. So the first is retrieve is, I guess, like a more efficient way. So like basically this syntax is more general in the sense that maybe you want to have a more efficient retrieve protocol instead of like running verify a bunch of times and extracting. So I think that's one of the main reasons, I guess. Yeah, good question. Good. Okay. All right. So I'll go just at a high level of what properties we want from a data availability sampling scheme. The first one is completeness. This is the usual thing you would expect, which says that the verify protocol and the local repair protocols should succeed if the dispersal is honest and most of the nodes in the system are honest. So this is the standard notion. Then we have two notions of soundness which capture actually slightly different guarantees. So we have something called worst case soundness. Actually this will relate to your question, Avi, but I'll come back to that. So we have two notions of soundness which actually capture slightly different guarantees. The first one is called worst case soundness. So what this is saying is even if literally everyone in the system was corrupt, like the disperser and all in storage nodes, Even in that case, we want to have some guarantee which says that if enough verifiers output 1, meaning that they believe that the data was available, then actually extraction should work from their transcripts. So this is sort of saying that like even if everyone is corrupt, if verifiers accept, meaning that somehow over the network they were able to get the chunks that they required for, then I can extract from their transcripts, meaning like there is enough information in the network. So that's sort of like the first thing we capture. The second guarantee is optimistic case soundness. So this is actually more related to retrieval in the future. So here we sort of imagine, so here sort of the key thing to observe is like if for example everybody was corrupt, then you cannot expect to be able to retrieve in the future because the corrupt nodes are actually not storing anything. They just reply to you during verify and then just shut down. So to capture that sort of scenario, we define a separate guarantee which is optimistic case soundness, where we say that if enough verifiers output 1 and if a lot of the storage nodes are honest, then we should be able to retrieve the data in the future. And sort of the intuition why is like if not a lot of storage nodes are honest, then we anyway have no hope of retrieval because there's very few people actually storing the data. So these sort of like two things capture slightly different guarantees in the system. This is like extraction during verify, and this is saying at any point in the future I should be able to retrieve. Any questions on this?
For the second one, do you need the first part of the state? Like, do you need the verifiers to all? Like, isn't it enough for this world to be honest?
That's a good question, but the problem is what if, so in this scenario, optimistic case soundness, the disperser could still be corrupt. So you can imagine a scenario where a lot of nodes were honest, but the disperser never even gave the data out, right? Yeah. So actually, yeah, that's actually a good point. So I should mention like in DAS in general, one of the very distinguishing factors is that the disperser could be corrupt. And like we want these guarantees to hold even if it was corrupt. Yeah. So sort of like verifiers outputting 1 sort of tells you that the disperser must have given out some chunks over the network, otherwise verify wouldn't work. Good question. Okay. So I will not go through the formal definition just in the interest of time. So now let's move on to the second part, which is a generic framework for building DAS, which supports local repair by construction. And there are 2 building blocks here. So let me first, okay, so let me just start with this first. So this framework is building on a framework which was proposed by a prior work, Hollanderson et al. In 2023, where they show that in general, you can build DAS from an erasure code plus an erasure code commitment. And what we're saying basically is to achieve local repair, we should have some notion of repair in both of these building blocks. So I want to use a locally correctable code which has repair, and we should also have a commitment scheme which also has repair. I will formally define all these in a few minutes. Then we should be able to actually get DAS with local repair. So let me start with the previous framework first. So then like looking at our framework will be easier from that point on. Okay. So a quick primer on erasure codes, though I'm sure everybody already knows what they are. So an erasure code is a pair of algorithms, encode and decode. So encode takes as input on a bunch of data. You can think of it as a vector of length k, and it outputs an encoding, which is capital E. This is a vector of length n. And then we have a decode algorithm, which takes as input a subset of the encoding E. So I'm denoting that as E hat. And then it outputs back that original data that you encoded. So let me show you this pictorially. So we have data, this is a vector of 5 elements. You can encode the data and get a bigger vector E. And now the guarantee that decoding gives you is that even if you lose a bunch of symbols, so let's say you lost E2, you lost E5 and En, what decoding tells you is even if you have, like as long as you have enough symbols remaining, actually I can still run the decode algorithm and get back the same data that I encoded. So this is the standard erasure codes. And in terms of notation, I will use capital delta to denote the minimum distance of the code. This sort of tells you how many symbols you need to be able to decode. Any questions on this? Okay, so this is the standard notion of erasure codes. So that's the first building block. Let's now talk about erasure code commitment, which is sort of like the second building block for building DAS. So erasure code commitments is a special type of commitment. This was formally defined by Hollanderson et al. In 2023. And sort of the key idea is that this commitment scheme allows you to commit to data with respect to a particular code C, such that we can do opening proofs for any position of the encoding. So we have 4 algorithms in the syntax. We have setup, which gives you some commitment key or the CRS. We have the commit algorithm, which takes as input the commitment key along with the data and gives you a commitment. So again, this is going to be the public reference or the paperclip from before. Then we have the open algorithm, which gives you the proof pi I for any position I that you want to open. And sort of the key thing I wanted to observe is like in C verify, It's taking as input the commitment, the position I and EI. So it's opening to the ith position of the code word, not the data. And then this checks whether the proof was valid or not, so it outputs a bit. Any questions on the syntax of erasure code commitments?
There's no mention of the erasure code of the two other algorithms?
Yeah, I think so. I just parameterize it with respect to a code C. So the syntax itself won't show you the code, but the definitions will, if that makes sense. The secret definitions will. Oh, I think Fan has a question. So EI is the ith position. So if I go back, yes. So to answer your question, Fan, if E was your encoding, I'm denoting E as a vector of symbols E1, E2, E3 to En. So as an example, if you think about Reed-Solomon, then EI will be the evaluation of the polynomial at I. Does that answer your question?
So here I ranges from 1 to the length of the encoding string in the next phase.
Yes, yes. So I'm actually, so I'm making a simplifying assumption for the talk, which is that the number of parties is the same as the length of your code word. So it's just n for both, just to simplify the talk. But in the paper we show you like you can do it more generally as well.
Can you say more about how that is different from just a regular vector commitment?
Oh yes, yes, exactly. So that's actually my next slide. So yeah, that's a good segue. Good. So very good. So yeah, so in the next slide I'll answer that. Okay, so this is the syntax. As Fan has pointed out, this looks a lot like vector commitment. What is the difference? Good. So now let's see what properties we want from erasure code commitment, and this is where we'll see why this is called erasure code commitment and not a vector commitment. So the first two properties are the same as vector commitments. We want correctness, which means that you honestly generate a proof for a position I, you should be able to verify. The second property is also the same as vector commitments. This is just position binding. It says that no adversary should be able to open the commitment at some position with two different values. But the key differentiating aspect is something called code binding. So what code binding is saying is that you should only be able to commit to valid code words for your code C. So a bit more formally, no adversary should be able to produce valid openings for a set of positions such that they don't actually match any code word. So for example, if you just use a vector commitment, then I can commit to any vector even if it was actually not a valid code word. So that's sort of like the key property we want. Yeah. Sorry, could you say that again? It is strong. It could possibly be stronger. Yes, yes, that's true. Yeah. I think just for like more intuition, I guess. Like it looks like the most natural thing you could define for something like erasure code commitment. And yeah, I think like I'm forgetting. Like there is like a formal proof to prove like the relation between the two. And I think code binding probably doesn't directly imply position binding. It's like code binding plus something else probably implies position binding. So it's not completely stronger. But I'll double check. Yeah. Yeah, I'll get back to you on that. Yeah, good question. Okay, so the third property is sort of like the key property which distinguishes erasure code commitment from usual vector commitments. Any more questions on the high level?
Yeah, I have a question. If you go back to the interface.
Yes.
I'm still a bit confused why the commit. So is there an implicit erasure codes to underlies this? Because like you basically commit only to the data, so without before encoding them.
Oh, good, good. Oh, I see, I see. So this, when I construct an erasure code commitment scheme, it is with respect to a particular code. So does that make sense? So like when I, for example, the commitment scheme I'll show in the end is an erasure code commitment scheme for multiplicity codes. Does that make sense?
So it has to be deterministic scheme. Otherwise, you don't know what your code is going to look like.
Right. Yes. So yes, that's a good question. So actually for today's talk in DAS, we don't care about hiding as much. So I will only be looking at binding commitment schemes, which means you can use deterministic commitment schemes.
Right. And yeah. Like how many, the parameter n is implicit as well?
N is implicit. Yeah. So for example, if you think of KZG, I can take an example. So KZG commitment scheme is an erasure code commitment scheme for Reed-Solomon code, because you can Reed-Solomon code, like you encode the data as a polynomial, and I can commit to it with the KZG. Yeah, and then the number n is, so I guess n is actually flexible, but the length of the data k, that is like implicit. So like for example, when I do KZG, the maximum degree is sort of like the data length that I can commit to, right? So I'm not like defining it completely formally here, but like there are some parameters that you use to parameterize this. Yeah, good question. Any more questions? Okay, so I will move on. Yeah, so these are the properties. You can look at the paper for the formal definitions. These are sort of like just the high level intuition. Okay, so now we're ready to see how we can combine these two building blocks to get DAS. It's like relatively straightforward. Okay, so how do we build DAS from these two building blocks? So the main thing is, what does a disperser do to disperse the data? So the first thing it will do is, of course, encode the data with the erasure code and get an encoding E1 to En. The second thing it will do, it will also commit to the data using the commitment scheme. So the commitment becomes your public reference or the paperclip. Then one more thing it will do is it will compute opening proofs for every position of your encoding. So we'll get proof pi1 for opening E1, proof pi2 for opening E2 and so on. And then storage node 1 will store the symbol E1, so the first symbol of your encoding, plus the opening proof pi1 for that symbol. Similarly, node 2 will store E2 and pi2 and all the way till N. Sorry, yeah. Any questions on this? Yeah, any questions on this? Okay. So now let's quickly see how verify and extract would work for a DAS scheme like this. So verify, as we already saw before, basically you just query random chunks. What that means in this framework is that I'm querying random positions of the encoding. So for example, maybe I'll ask node 1 to give me E1 pi 1. I can ask node 3 to give me E3 pi 3, and again the last node to get En pi n. And then I'll output 1 only if all of these opening proofs are actually valid with respect to the commitment. So this sort of answers the question I think you had before, that there's like the proofs actually let you check consistency with respect to the commitment scheme. So you know that these chunks actually correspond to what was committed before. Good. So yeah, that's how verify would work, just at a high level. And extraction is also sort of straightforward. So again, recall and extract, we have a bunch of transcripts from a lot of verifiers. So for example, this verifier in the picture, in its transcript, will already get symbols E1, E3 and En. But now if there was, let's say, another verifier in the system, maybe it got E2 and E5 and En minus 1, like a different subset of symbols. So essentially, as you have more verifiers, slowly you'll have like you'll collect a lot of symbols of the encoding, and then you can run the decode algorithm of your code to get back the original data. Any questions on the framework? Yeah. Oh, so yeah, that's a good question. So like if you think about this example, right? So what every verifier is doing is sampling a small set of chunks, right? So one verifier on its own actually doesn't really get any guarantee that the data is there, because it only knows that 3 chunks were there. And like if you think about the code, then 3 chunks, like you can't decode with 3 chunks, right? Like for depending on how large your data was. So actually in data availability sampling, the soundness guarantee necessarily requires that there are a lot of verifiers. Each of them randomly samples a bunch of chunks, and the hope is that in aggregate we actually sample enough chunks that now we can decode. Yeah. So I guess just to rephrase, you're saying like maybe if each verifier samples more chunks, we'll need less verifiers. Yes, exactly, that's true. But I think in general in the DAS, at least in the practical setting, what we want is the verification to be very efficient. So we don't want to like do a lot of verification. Yeah, because like that's what like beats the whole point of like doing this in a distributed manner. So yeah, just for an efficiency thing, we don't want every verifier to do like a lot of sampling. But definitely the soundness will be stronger if like I do more verification. Yes, good point.
What are the typical parameters, like how many chunks?
Like 200 or something. So like you.
Constant compared to N?
Yes, it will actually be constant. Yeah.
And then how many verifiers?
Verifiers, let's see. So there's, like for example in Ethereum, like there's like tens of thousands of validators, and usually you can imagine like at least, for example, at least 10% of them are verifying, so maybe like 1,000.
So constant fraction of verifiers,
right?
And each verifier verifies a constant number of.
Yeah, I mean, okay, that's a good point. I think we can think of them as like polylog parameters or something.
Okay.
So yeah, basically like I'll show you like the theorem statement. So like we parameterize the security guarantee as a function of how many verifiers you have, what percentage of them are verifying, and so on. So like the soundness you're getting depends directly on that. Yeah, so like definitely if you're implementing this, you should tune your parameters based on the soundness guarantee, for sure. Yes, good point. Okay. So yeah, so that was like a very high level picture of how you can build DAS from an erasure code and a commitment scheme. As an example, what Ethereum has implemented in Fulu, they encode the data using Reed-Solomon, just a univariate polynomial, and then they use KZG commitment to commit to the data. And now we can move on to our question, which is how do I repair lost chunks? So in this picture, this is the same framework as before. Now the question is what happens if the last node loses its data? So now the question is, in this framework, I need to be able to efficiently repair the chunk EI, which I lost, plus the proof pi I. So I need to repair both of the things. And that's sort of the key question that we'll solve next. Okay, so we have two building blocks. The first one is locally correctable code. So this will basically allow us to repair EI, and the commitment that we define will allow us to repair pi I. So that's what's going to happen. But let me start with locally correctable code first. So basically, locally correctable code is a special type of erasure code which has been studied in the coding theory literature, where we can repair any position of the encoding by only querying a few other random positions. So pictorially, let's say this was your encoding. Let's say you lost the last symbol. So if R, which is the parameter for your code, was 2, for example, then you'll be able to repair En, the symbol En, by just looking at the symbols E1 and E5. So in this particular example, let's say the naive way to do repair would have been to collect a bunch of other symbols and run decoding. But now because I can because I have local repair, I only need to query 2 other symbols, and that's actually all I need to be able to repair. Yeah. Yes. Exactly. Exactly. Yes. Exactly, yes. Oh, sorry, I was supposed to go the next way. So yeah, as an example for you, if you think about Reed-Solomon codes, they're actually great codes because their minimum distance is actually optimal, but their locality is actually very bad. So in Reed-Solomon codes, the parameter R is equal to K, which is the data length. So it means you literally have to query, like let's say if your polynomial was degree 1000, you actually have to query 1000 points to be able to repair. Whereas if, for example, R, like depends on what R is for your scheme. For example, let's say it's 10, then you only have to query 10 points, whereas in Reed-Solomon you have to do 1000. Yeah, good. Any other questions? Okay. Very good. So just like a bit more formally, we have the encode algorithm, decode algorithm, but we also have local correct. So local correct also takes a bunch of symbols from your encoding, but like much fewer symbols than decode, and then it will give you EI, which is the ith symbol of the encoding. Okay. So yeah, that was the first building block. The second one is erasure code commitment with local correction. This is what will allow us to repair the proof pi I. Okay, so this commitment scheme is a special type of erasure code commitment where we have this extra property of local correction. So again, we can repair the opening proof for any position of the encoding by querying the opening proofs of only R other random positions. So this is the picture we had for the code, and what we would like is the same property for the commitment scheme. So again, if you lose symbol pi n, ideally we'll only need the opening proofs for symbols 1 and 5, so pi 1 and pi 5, and hopefully we can just compute pi n from these two symbols.
Does it mean that if we only have XR centuries of the code, then we can recover the original?
Sorry, say that again?
Because then from our elements,
yes.
Then we can recover the value.
Oh, no. So it's a different set of R positions for, so like if I want to repair n, I'll probably need 1 and 5. For example, if I need to repair n minus 1, maybe I'll need 2 and 7. Yeah, a different set, yeah. So like, because, yeah, of course, because like any R symbols won't have enough information to be able to repair everything, right? So like, they can repair certain symbols. So there's like it depends on your code, like which symbols can repair which symbols. Yeah, good question. Okay, so yeah, that's an erasure code commitment with local correction. This is a new primitive we introduced. And just in terms of syntax, we have the same for algorithms as before, but we also have C local correct, which takes as input a bunch of symbols EJ of your encoding, along with the opening proofs pi j for the same positions, and then it gives you the opening proof for I. Any questions on?
Yeah, another follow-up question. So,
okay.
Does that mean that you need only 2, let's say, positions in order to do the
for example,
right? Yeah. But in aggregate, in order you need at least K to exist.
Yes.
Information theoretically.
Yes, exactly. Yeah. So like for retrieval, the requirement for retrieval still remains the same. I will need K, at least, or like minimum distance number of symbols, definitely for retrieval. But what repair is saying is like, at least I can repair some chunks of the system just for better fault tolerance, or like to avoid griefing attacks.
Right, but for repair,
yes.
you only need 2, which is
for example,
less than k.
Yes.
You still need k present to sample from.
Yes. You still need k to sample from, okay. And again, this is 2 just because I'm trying to repair one symbol, right? I'm not trying to reconstruct the whole thing. Just to repair a few chunks that you lost, I like immediately repair those with 2. Yeah, good. Oh, okay. Oof. I should rush now. Okay, so yeah, in terms of properties, we define something called local correction, which sort of says the same thing. Like if I can repair the code, I should also be able to repair the commitment. Okay, so I will.
It's always the same indices that you need?
Yes. So that would be ideal, right? Because like we don't want, if it was different indices, then that will mean I'm like doing double the work on the network because I'll have to ask like let's say 1 and 5 for the symbol and like 2 and 7 for the proof. So ideally it should be the same set of symbols. Yes, very good. Okay, so I guess quickly going through the framework. Basically the framework looks the same as before, but I'll be using a locally correctable code to encode the data and then a locally correctable erasure code commitment to commit to the data. And now, for example, if the last node lost its data, it can only query, it just needs to query nodes 1 and 5, and then it has all the information it needs to repair en and pi n. Good. Okay, so yeah, this is the formal security statement coming to your question. So here L is the number of verifiers, delta is the fraction of verifiers that need to accept for a soundness guarantee, and then we have like something on the distance, and Q is the number of queries that every single verifier does. So we have this statement of like, okay, this is your statistical security guarantee based on all these parameters. Good. Okay. Yeah, so just one thing I want to mention is like the network itself, like gossips up, we had to formalize the properties that it gives you to be able to actually guarantee retrieval, and you can find some details in the paper. Okay, so I do want to cover our construction, which is multiplicity codes plus a new commitment scheme. Maybe I can go over time a little bit. Okay. Sorry. Okay, yeah. So before I do that, I guess this is also an important slide. Okay, so I just want to briefly mention that we have seen this framework now. It has a locally correctable code plus a commitment scheme. But so the key question is what type of code should I be using and what type of commitment should I be using to get an efficient DAS scheme? And to do that, let's analyze the metrics that we saw before. How do they depend on the choice of the code and the commitment? So for example, node storage, what we saw in the framework was that every node will store one symbol of your encoding plus one opening proof. So this tells you that if I want to have small node storage, then my commitment scheme should have small opening proofs. Then we can keep going. For disperser work, the disperser has to do encoding of the code, plus it has to do the opening proofs for all positions. So what this means is we would ideally like to have a batch opening algorithm for the commitment scheme. So this part is efficient for the disperser. Repaired complexity means we should have efficient local correction for both of them, meaning R should be as small as possible. And then sampling bandwidth, actually we show in the paper, it depends on the minimum distance of your code. So sort of intuitively, the better the distance, the less you have to sample, because you can decode from less symbols. So this is sort of like the key thing here, like we want to co-design locally correctable codes with the corresponding commitment schemes to get efficient DAS. And that's why we chose multiplicity codes and we designed a commitment scheme that is compatible with multiplicity codes. So let me briefly tell you about multiplicity codes before we see our commitment. So these codes are a generalization of Reed-Solomon and they were proposed by Koparty et al. In 2014. Here you interpret the data as a multivariate polynomial of some degree. So data is f of x comma y, we'll think about bivariates for today. The encoding of the data actually contains the evaluations of f at a bunch of points. So this is the same as Reed-Solomon where you have the evaluations at a bunch of points. But the extra information that actually we have is we also store derivatives of the polynomial. So we have f prime x, this is the first derivative with respect to x. And we also store the evaluation of this polynomial at all values of x and y. Similarly, we have f prime y, this is the first partial derivative with respect to y. And we also store its evaluations at all points x comma y. So pictorially, the first symbol of your encoding E1 would contain the evaluation of f at the point 1 comma 1 along with f prime x at the same point and f prime y at the same point. And this is sort of the first symbol of the code which the first node in the system will store. And you can sort of keep going, you have 1 comma 2 all the way to 1 comma q, and you can complete the matrix. You have like all points from 1 comma 1 to q comma q. The two key properties of multiplicity codes which I want to highlight are first, they actually have good minimum distance. And do you have a question or? Okay. And this is an implication of the fact that we are storing derivatives. So basically derivatives give you extra information about the polynomial. So even if you lose more symbols, I can still repair because I have the derivatives. So that's sort of like a simple way of understanding why it has good distance. And the second property is that it has good local correction, which was sort of the key goal of today. So to show you why that is the case, let's take the example that we lost EQ, the symbol in the first row. And for this, let's look at the first row in particular, the thing I've highlighted in the green rectangle. We have the evaluation of f, the bivariate polynomial, at point 1, 1, 1, 2, all the way till 1, q. So I can actually think of these evaluations as the evaluations of a univariate polynomial f of 1, y. And because the overall degree was d, this polynomial also has degree d. What that means is if I get d plus 1 points in this row, which are d plus 1 evaluations of this univariate polynomial, I can actually compute f of 1, q. So that sort of tells you that any d plus 1 symbols in the first row are actually enough to repair that symbol that we lost. And this is also true for the derivatives because there are also degree d polynomials. And what's better is that you can actually do this along any line. So you can take the diagonal, and again you can see that the evaluations on the diagonal are a univariate polynomial of degree d. So again I can recover. And you can also do this on the column. Any questions?
Here, are you assuming that Q is like root n?
Yes, good. Yeah. So Q will be roughly root n. So the degree, roughly like d square will be k. K is the data length. So d square is usually k. And Q will be close to d. So yeah, like asymptotically it's close to root n. Yeah. Oh, okay. All right, I should rush now. So yeah, I'll say like we also have like an efficient encoding algorithm in the paper for multiplicity codes, which as far as we know didn't exist before. Okay, so now let me move on to the last part, which is a new polynomial commitment scheme. So again, before I move on, the key thing here is I'm now using multiplicity codes to encode my data. But now I need opening proofs, which let me verify the derivatives, which are there in every symbol of the encoding. So, and along with that, I need like efficient local correction, I need efficient batch opening for my DAS to be efficient. So a new commitment scheme achieves exactly all these three properties. This is a new multivariate polynomial commitment scheme, which has efficient opening proofs for the evaluation of a multivariate polynomial and its derivatives. So for example, for bivariates, for first derivatives, the proof size is just 3 group elements, and we just need 4 pairings to verify. We have an efficient batch opening algorithm to compute all opening proofs. We generalize Kovarodovic Feist to multivariates for this. And lastly, we have an efficient way to locally correct opening proofs, which is important for repair. So I will try to cover this if possible. So our commitment scheme uses PST as a starting point. So just as a refresher on PST, we are dealing with groups of prime order P. We have a symmetric pairing, E, which goes from G cross G to GT. And in setup, we have all powers of tau. So because we're dealing with bivariate polynomials, I have tau 1 and tau 2. And my CRS will have all the monomials tau 1i, tau 2j in the CRS. And then to commit to a polynomial, the commitment is just f evaluated at the secret point tau 1, tau 2 in the exponent. Just a generalization of KGG. And then I guess the main thing here is to open this commitment at a point a comma b. What we do is we compute quotient polynomials q1, q2 such that f of x comma y minus f of a comma b is equal to q1 of x comma y times x minus a plus q2 times y minus b. So this is just like an algebra thing, like this equation is true, like we know that q1, q2 exist for any f, and the idea is that these q1, q2 act as the opening proof. So the proof will be q1 at the trapdoor and q2 evaluated at tau. Any questions on PST? Okay, and yeah, I guess to verify, we just check exactly this equality in the exponent. So that's what happens with verify, we use pairings for that. Okay, so now I will show you the last part, which is, so this is just the verify for PST, let me skip through. Okay, yes, we are back. Really sorry about that. Okay, so this is the last part. I'll just this will be hopefully the last slide. Okay, so sort of the only key thing I want to show you is how do we do derivative openings. So we are in PST, and what we want to do is prove that the derivative f prime x evaluates to some particular value y at a point a comma b. So that's the goal of this slide. So the key thing here is we'll start with the opening equation for PST, which is f of x comma y minus f of a comma b equals quotient q1 times x minus a plus quotient q2 times y minus b. And now the main thing we'll do here is we'll actually take the derivative on both sides and we'll apply the chain rule, some fun calculus. So on the left side we'll get the partial derivative f prime x of f at x comma y. So this is the left hand side, just taking the derivative with respect to x. On the right side, if I take the derivative, actually what I get by chain rule is q1 of x comma y times 1, because the derivative of x minus a is 1, plus we get x minus a times the derivative of q1. So this is just if you apply chain rule to both sides of the equation, and the remaining terms, they don't have x, so they just go to 0. So this is one of the key relation we get if we do derivative on both sides. But now the very nice thing is if I put x equals a and y equals b, so this is the point that we are trying to open. What we get in this equation is that the value f prime x at a comma b, so this is the evaluation of the polynomial we're trying to prove. Turns out this is exactly equal to the evaluation of q1 at the same point a comma b. So this is like an application of L'Hopital rule on multivariate polynomials and gives us this very nice equality. What this equality implies is to prove that f prime x at this point is equal to some value y. All I need to do is I need to prove that the quotient q1 opens to that value at the same point. So what I can do is I can compute quotient polynomials q1a, q1b, just like PST opening for q1, and these two elements will act as the opening proof for f prime x. Any questions on this idea? Okay, so that's sort of like the first core observation, that how we can do derivative opening proofs. So it turns out if we do the same thing for y, you get actually that the derivative f prime x, f prime y at the same point equals the second quotient q2 at b. So I won't go through like the exact equation, but turns out this is actually true. So now this means to prove the evaluation of f prime y at the same point, I can just open my second quotient q2 at the same point. So again, I'll open, this is just case g because it's univariate. I can just compute q2b, and that will be my opening proof for f prime y. Any questions? Okay, so yeah, I will rush through this, but basically combining it all, you can have opening proof for f, for q1 and q2, and you can verify by checking the 3 opening equalities for the 3 polynomials. There is one more optimization we do. So like if you naively do this, the proof will have 5 group elements, and pairing, actually for verification you actually need 8 pairings. But what we observe is we can actually combine all the equations, and that allows us to have a proof size of just 3 group elements, and verification will only need 4 pairings. So yeah, maybe I can talk more about this offline if you're interested. Okay, so this is like just a formal proof statement. We prove position binding actually based on the same assumption that PST relies on, so strong DS bilinear Diffie-Hellman. And yeah, so let me just conclude. So in this work, we saw new definitions at a high level. We saw a generic framework to get DAS with local repair, and we saw a new construction using multiplicity codes plus a new polynomial commitment scheme. And again, the efficient batch opening was also really fun to do. Like we extend Korodovic 5 to multivariates, and that involved a lot of algebra. And the second is efficient local correction for opening proofs as well. So you can find more details in the paper. And yes, so to conclude, hopefully I've convinced you that local repair and data availability sampling is an important problem. And what we saw today was one way to get DAS with local repair with these 2 building blocks. I think there's like good open questions in this space, which is you can use other locally correctable codes, like the coding theory, there are a lot of other options, but we would also need to build the corresponding commitment schemes, and that's like the fun crypto question for us. And lastly, sort of mechanism designed to support data availability sampling is also an interesting open question. Yeah, thank you, and I can take questions now.